So, hello everyone. This is a Dr. Irshad Ahmed Khan from Department of Mechanical Engineering, Sagar Institute of Research and Technology, Bhopal. And today we will be discuss here how to calculate or how to derive the formula for Euler load for the different boundary conditions. And let's see. The first boundary condition is if the both ends of this column are hinged or pinned. So what would be the relation for Euler load? So let's see this. You can see this diagram. Initially, this was a straight column. When we applied the load from P in upward, so it's a buckle like this, and this is called the elastic curve. So um, we can take a section xx from um, uh, at a distance x from this bottom end, and the deflection of this elastic curve is y at this section. So we know that already. We are familiar with this equation. This is called the equation of bending of beam. So this equation is EI d square by upon dx square is equal to m, where m is the bending moment. So we can say that bending is the bending. You can see we can calculate the bending moment by the maximum displacement at this section. So how we can find? So this is a load P is acting, and what is the distance of this this point? So maximum displacement is y we have taken. So P into y would be the moment or buckling or at this point at the section where we have taken. So let's see. We can write P into perpendicular distance to Py. So why we have taken minus sign here? Because we have already discussed in the previous lecture. So if this concavity is formed, so we have take the minus sign. So that's why we have taken the minus sign. So this now the new equation we can write as EI d square by dx square plus Py equal to 0. Mm, Py equals to 0, and then now we can divide the in whole term by EI. So we can write d square y upon dx square plus Py EI is equal to 0. And what we can do, right? uh, we can write this term P, this one, this P upon EI equal to alpha square. Okay, so alpha square. So now this equation become d square y by dx square plus alpha square y is equal to 0, where alpha square is equal to P upon EI. So this is a new equation. You can see differential equation. So if we know the how to solve this differential equation, so let's see what would be the solution of this differential equation. The solution of this differential equation is y is equal to a sine alpha x plus b cos alpha x. So this is a solution of this differential equation. Okay, so let's put the boundary condition, or we can say end condition, in this equation and find the value of a constant a and b. So first you can see where x is equal to 0. X is equal to 0 means here if the x is equal to 0, so here the y is equal to 0. Y is deflection. You can see there is no deflection at the pinpoint. So we can say, you can put that value x is equal to 0 means this term, the you can see that the sign 0 is 0. So this y is also 0, and this cos 0 is 1. So we can say b is equal to 0. So similarly, we can see x at x is equal to L means here at the point B. So we can write x is equal to L, y is equal to 0. So at x equal to L, y means deflection is also 0. And so we can say, so put the value of these x is equal to L by, so it would be z, it would be the value, it's 0, and this x is L, so we can put the value of L, and we all also know that b is equal to 0, so the term becomes 0. So we can write a sine alpha L equal to 0. So you can see in this equation, if a is equal to 0, so y is 0 for all value of load. If it is happen, so there is a no bending takes place. So this is not true. So a can't be equal to 0. So which part is 0? This part, sine alpha L equal to 0. So what would be the solution of that? The sine value is 0 at the pi. Okay, so alpha L equal to pi, so alpha is equal to pi upon L, and we already written here alpha is equal to P upon EI. We have taken here assumptions. Okay, replace this term by alpha square. So here we can write is equal to PE, which is called the Euler crippling load. Here, Euler load is alpha square EI. Put the value of alpha, then now it's become pi square EI upon L square. And this relation is called the Euler crippling load when the column is subjected to both end as a pinned or hinged. And second case is one end fixed and another end free. So we can see this diagram. If B part, this part is free, if we apply the load at the end, so it will be bent like this. So you can see buckle like this. So we can see, my dear students, the same way we have can take the section at exit distance from this fixed end, and at the present deflection max at this section x-axis is y, but it's the topmost condition, there is much deflection. That name we have taken, that is a, and that is total deflection, maximum deflection, you can say a. And you can see from this point to maximum displacement point, we can write a minus y. Okay, so we all know that equation of bending, like I d square y dx square is equal to m, and we can see that a p, this is a p maximum load, and is this point from the where the section we have taken, and the perpendicular distance is how much is a minus y. So we can put is p a minus y, but this is a case of convexity, so that's why we have taken here plus sign. Okay, so now rewrite this equation. EID square y upon dx square plus py is equal to PA, and we can write this equation just by dividing the EI in the whole term. So this would become like this, and again what we are going to do, replace this term by alpha square. You can see this. So this term become PA upon EI at the right side of the equal sign. So now we know that alpha square is equal to P upon EI. Okay, so in the next slide, we can say what would be the solution of this equation. So this one, so the solution of this equation would be y is equal to a sine alpha plus b cos alpha PA upon EI alpha square. This whole term, you take that whole term PA upon EI, then divide by alpha square. So just put the value of alpha square. We all know that alpha square P upon EI. So put the P upon EI. So here PP cancel and EI cancel. So now only here A remain. So now this equation become A sine alpha x plus B cos alpha x plus A. So now you can see, because this end is a fixed, so here if at the fixed end, slope and deflection both are 0, and here x is equal to L and y is equal to equal to AK. It is equal to A. Okay, so let's see the first one. It's a first end condition. So x is equal to 0, y is equal to 0. Okay, we can see here, we can see x equal to 0 and y is equal to 0. So put the all value. So this will be 0, this 0, and this term is 1, cos is 1. So we can say v is equal to minus a. Now, the at x is equal to 0, so deflection is also 0. So we first I first we will differentiate it and then put the end condition. So differentiate this term is so dy upon dx. So dy upon dx. So this term, this would be a alpha cos alpha x minus b alpha sin alpha x equal to 0, and then put this value. So x dy upon dx is equal to 0. So you can see one term is basic. So we can write here equal to dy upon dx equal to a alpha cos. So like this. So you put this value, and so it's become 0. And and you have to be put the x, you replace x by 0. So this will 0, and because you can see this is 1 and this term is already equal to 0, so this will be a is equal to 0. Hope we understood. So let's see if we got both value of a and b and put in this equation, number 1. So we have we got y is equal to a minus a cos alpha x plus a. So we can take a as a common, 1 minus cos alpha x. So if again we have to put the value x is equal to L. I already told you that this, you can see that at x is equal to L, that y equal to AK. So just put in this equation, you can put value of y is a, and in place of x put the L. So it's become cos alpha equal to 0. Okay, so now we know that cos value, where the value of cos is 0, at the pi by 2. So we can write alpha is equal to pi upon 2L. Now the Euler Crippling load P is equal to, we know that the alpha square EI we take from here. Okay, so now put the value of alpha. So it's become pi square EI upon 4L square, and this is a relation. This is Euler relation for a column which one end is fixed on another end is free. And you can write this universal equations like this for Euler coupling. If Euler coupling load, that would be the pi square EI upon 2L square, and this can be also rewrite pi square EI upon LE square, where L is equal to 2L and L is called the equivalent length. So this is two questions today we have discussed, and coming class we will discuss the remaining case. So thank you so much for listening this video lecture.